So this is Tackling Climate Change with Machine Learning and David Rolnick.
Thank you so much for having me. I'm happy to be here. For reference, I'm a professor in the School of Computer Science and also part of MILA, which is this collective of machine learning folks from different institutions around Montreal. I'm also one of the chairs of Climate Change AI, which I'll talk about a little bit at the end. It's a facilitating organization at the intersection of climate change and machine learning. Let's get started. So given everybody's background, I figured I would start out very briefly with what climate change is, though I don't think it needs that much introduction. So climate change is a problem for humanity with increasingly severe effects, which we're starting to see more and more. So there are a lot of different effects of climate change. And I'm going to go into them in a little bit of detail, only a little bit. So there are storms. Let's just unpack each of these things and why it's connected to climate change, like very, very, very quickly. So storms are getting made more numerous, as more frequent, and stronger as well. And that's a result of climate change changing temperatures, but also ocean circulation patterns and airflow and stuff like that, changing precipitation patterns. So for example, like warm water sticking around in portions of the ocean can lead to an intensification of hurricanes in the Atlantic. So this flooding comes from a bunch of different reasons. So people often think of flooding from climate change because of sea level rise, but it's actually there are a bunch of different things. So flooding comes from sea level rise. Sea level rise itself comes from two different things. It's not just melting snow and melting ice. It's literally the ocean expanding too. So when you heat up something, it expands very, very slightly generally, but the ocean has actually absorbed 90% of the heat that has been a result of global climate change, of a warming climate. So 90% of the heat we are not feeling in the air because it went into the water. There's just a lot of water and it's really good at absorbing heat. And that meant the ocean expanded a little bit. And since the ocean is super deep, that means that sea level rises also because the ocean literally expanded. And that's another reason why it happens in different places at different amounts. And then there's also flooding as a result of those powerful storms. So that happens inland. It also happens, when a hurricane comes or something, and it causes flooding on the coast because the sea level is higher, but also you have brought in a powerful storm. There's extreme heat, which is so extreme that it sort of changes the extremes. Climate change, the thing of like changing the distribution, making it more likely to get scary kinds of weather and extreme events. Heat waves getting stronger may not matter as much here, but if you're in the Middle East, it may be extremely bad. And it's predicted that by 2100, much of the Middle East will be actually unlivable by people because of the sheer amount of dangerous heat. And then there are droughts, which are a result of both heat and also changing rainfall patterns. And droughts can also result from melting glaciers. So many parts of the world, in particular, places near mountains will rely upon like mountain-fed rivers. There are many places that don't get rainfall during the summer, but do get a lot of meltwater from glaciers. So like a lot of agriculture that is near mountains relies upon meltwater from snow in the mountains. And if there isn't as much snow, or if the glaciers have melted, then that can be catastrophic for people and for farming. And then there's fires. So fires is complicated. There are three ways in which big fires that make the news happen, and not all of them are climate change. Most of them are climate change. The first one is fires in places that really shouldn't have fires. That's like fires in Siberia, where you wouldn't expect there to be fires. That's because of climate change. Then there are fires in places like California, where you would expect there to be fires. These places naturally have fires, and it's partly due to bad forest management and partly due to climate change, because climate change is making it easier for those fires to occur. The third reason, and I am going to eventually get onto the machine learning, but I wanted to frame the topic of climate change. Third reason why fires occur is because people set them. That's what's happening in the Amazon. I can't tell you how many times I've read that the Amazon burning is a result of climate change. It's not a result of climate change. It's a result of people cutting down the Amazon, deliberately setting it on fire. Now, it's actually making climate change worse because when you burn a forest, it releases carbon dioxide into the atmosphere. But it's not caused by climate change. It's not because the Amazon is warmer. It's because we're cutting down the Amazon. Okay, so that's the effects of climate change. That's why you should care, because of all these issues that are already killing people and are going to kill a bunch more. You should also care about it because it has uneven impacts. Now, that means, like any other catastrophe around the world, like COVID, the most disadvantaged people are hit the hardest. Places that are hit by climate change the most are those that are already more fragile. And that's just because of geographic coincidences, but also because of the way that the way that the more advantaged locations are always able to get out of some of the consequences, only some of them. There are also feedbacks. Now, feedbacks are really scary. They're basically saying, as we make climate change worse, it gets worse by itself. So first one of those, albedo, that means reflectance. Like if you melt snow and ice, the white disappears, and the white is actually reflective. And so if you take away the snow and ice from Earth, you end up with absorbing more sunlight, and that warms up the Earth even more. Another feedback is the permafrost melting. That is northern frozen ground, which melts and then releases carbon dioxide and methane, which are major greenhouse gases. And so in both of these situations, as the Earth warms, it starts warming even more. So what is causing climate change? The cause of climate change is human-made greenhouse gas emissions. So we particularly think about carbon dioxide. There's also methane, which is more powerful but doesn't last as long in the atmosphere. There's also nitrous oxide and a bunch of other things. And what we need is net zero greenhouse gas emissions by 2050, according to the UN's Intergovernmental Panel on Climate Change. And yet every year emissions are increasing. There is a slight blip this year due to the global pandemic, but hopefully, as that hopefully fades, the emissions are expected to go right back on track to increasing, barring considerable action. So not only are we not decreasing to zero, we are increasing. Okay, now, why is this a complicated problem? Why have we not already solved climate change? It's because there are just so many moving parts, and because of a bunch of other things, but it's not a single thing. It's not a single, there's not a single action we can take to suddenly fixing climate change. All these different sectors, here's transportation, here is electricity and heat, buildings and manufacturing, industrial processes, agriculture, land use, all of these things are contributing significantly, but there's no one, it's not like, if we stopped using airplanes, we would be fine. No, it's not even if we stopped burning fossil fuels for electricity would be fine, which is a bit more subtle, though that would be very, very powerful. There are a lot of different actions that we're taking which produce greenhouse gas emissions. Like 10% of the greenhouse gas emissions comes from just making steel and concrete. And that's a mixture of, heating these things using fossil fuels, and also literally when you make concrete, part of the process directly releases carbon dioxide. And these are the net greenhouse gas emissions. Most of it's carbon dioxide, like 3/4, and then there's a bunch that's methane and a bunch that's nitrous oxide. Most of the nitrous oxide comes from fertilizer breaking down. So that's when you use fertilizer in agriculture, that turns into nitrous oxide. Okay. So that is the problem of climate change. I'm getting to the machine learning in a moment. What does it mean to tackle climate change? I'm often asked, is it too late to tackle climate change? And I don't like this question. First, because if it were a yes/no question, the answer would certainly be yes, it is too late. People are already dying, more are already going to die, regardless of what we do. But it's not an on-off switch. We get to choose exactly how bad it is. And there is a huge difference between really bad, which is what we're guaranteed now, and really catastrophic, which is what will happen unless we do a lot more. And we do have it in our power to avert the really catastrophic. So there are two things that are required, very broadly speaking. There's mitigation, which is reducing greenhouse gas emissions, so stopping the problem from being the case. And adaptation, which is resilience to the consequences of climate change. So responding to the things that happen as a result of us having already emitted too many greenhouse gas emissions. Okay, so within this broad space of climate action, what is the role of technology? Now, we already have technology that you could argue, there's debate about this, but you could argue that our technology could already enable our society to have zero greenhouse gas emissions. So why do we need to do anything at all? Well, just having something is not, that doesn't mean that people will actually use it. There are good reasons why this technology has not already been adopted across the world, for cost reasons, for inertia reasons, for side effects reasons. There are a lot of really good and some bad reasons why we have not already fixed the problem. Tech is not as important as many other things in climate change. I'm not about to suggest that everybody who wants to work in climate change go work on tech, much less in machine learning. In particular, policy is exceedingly, exceedingly important. But there is a role for technology. In particular, technology can make the transition somewhat easier. So like it's not just good enough to have tech that could theoretically solve your problem if you were prepared to, cut off your arm and live in the middle of the desert for the rest of your life, and then we would solve climate change. Nobody would do that. So making the transition easier, less of a barrier, and also providing tools for other kinds of climate action, like policy. So these are the themes that we're going to see for ways in which machine learning can dial in. Machine learning is not like some savior that's going to fix all the problems, but it's going to fix particular bottlenecks within components of climate action. Okay, so if you're interested in this topic, we have this really big overview paper, Tackling Climate Change with Machine Learning. It's over 100 pages. I'll include a link at the end. There are interactive summaries of it online. So if you want to sift by area of machine learning that I'm interested in, or area of climate change work that I'm interested in, you can also do that. So you don't have to actually go through 100 pages. It is designed to be a bit more user-friendly than that. But I'd like to go over here some overarching themes that we see for how machine learning dials into climate change work, and so hopefully give you an idea of sort of what the points of intersection are. So the first point of intersection is distilling observed data, taking raw data and turning it into usable information. So this is often satellite images, remote sensing, or large bodies of text, so natural language processing. And the idea here is that there are these tasks which we'd like to gather information for, and having a person do that is just super time intensive and really difficult to scale. Some examples of this are tracking greenhouse gas emissions. So things like methane. Methane is particularly good because it's a very intense greenhouse gas emission, and it's often coming from concentrated sources like leaks in natural gas pipelines. And you can see those if you take satellite imagery with hyperspectral cameras. They can see methane. And pinpointing that using machine learning can be done automatically. A lot of these are sort of out-of-the-box computer vision tasks for those who have seen computer vision. Though in many cases, there are greater implementation challenges and also machine learning innovations that are necessary to make these solutions better. So gathering infrastructure data. In many parts of the world, we don't know where the buildings are. In North America, we, for example, don't know where the solar panels are, which means that we don't understand what effect they have on the electrical grid. And it's really important for managing the electrical grid to know where the solar panels are. So deep learning, for example, has been used to pinpoint solar panels or pinpoint buildings, predict the heights of buildings to understand what their energy use is going to be. Identifying deforestation as it happens. So saying this piece of a forest is being cut down, we can send law enforcement. Evaluating coastal flood risk. So this is an adaptation. So the previous things were mitigation, reducing greenhouse gas emissions. Deforestation contributes to climate change. energy use in buildings contributes to climate change. Coastal flood risk is an effect of climate change. And people have used machine learning to evaluate the heights of different pieces of land around the world, match that up with the differing amounts of sea level rise in different places, and work out how many people and where they are at risk from coastal flooding. And this has actually radically changed our predictions. Using machine learning, it's radically changed our predictions of who is at risk. And then from an NLP perspective, there's, for example, parsing company reports to get relevant info for policymaking. That's an example. So this overall theme is you have this big sort of unstructured database, and you'd like to pull relevant information out of it and do this at scale. So that's the role of machine learning here. In each of these cases, you should also be thinking about like who is going to use the machine learning in the end. So in that case, it's often policymakers. There are other circumstances, like electrical grid operators. Okay, improving efficiency. So this next overarching theme is in making a complicated system more efficient. Machine learning is really good at that, sort of tweaking little knobs in this complicated system and working out how to make it run more efficiently. And in many cases, this is to use less energy. Okay. The kinds of machine learning involved here are just the various kinds of optimization and some reinforcement learning, for example, and a bunch of other techniques. So the first example is in controlling heating and cooling systems efficiently. The heating of buildings and cooling of buildings uses a ton of energy globally. A significant fraction of global greenhouse gas emissions. Offhand, I think it's like 10%, 15%. Using less energy to do that is really important. Machine learning, it turns out, can control heating and cooling systems so that they use less energy while still maintaining the desired temperature. For example, Google did this, setting up a reinforcement learning algorithm for their data centers, where they reduced the energy required to cool down the data centers by a significant margin by just having a very good control system. Likewise, optimizing supply chains, everything from freight routing, so determining how freight should be routed and also helping to interface between different modes of transportation, like predicting train arrival time so that they can interface with trucks. Really sort of nitty-gritty stuff that is extremely impactful. Also reducing food waste. So having an ordering system that can predict how much food will be needed in a supermarket or in a restaurant and preventing that large amount of food from being wasted. Food waste is the third, if it were a country, it would be the third largest emitter of greenhouse gas emissions around the world. It's huge amounts of greenhouse gas emissions from food waste. And then another example being demand response in electrical grids. So in electrical grids, you need to have supply match demand. But supply of electricity is changing, especially with renewable energy, from point to point during the course of the day and night. There may be more wind available at night, more wind power, but there may be less demand for it. Demand response is sort of moving around demand, so when you're using electricity, to match the supply or the carbon intensity of that. So saying, there's lower carbon, more efficient renewable energy at night. For example, maybe I will move some of my some of my appliance usage to the nighttime, or move the charging of my electric car, stuff like that. This is already being done in some cases, but to scale it up, we really need a sort of flexible, smart electrical grid. And this is an area of applications for machine learning. So we've seen about optimizing complicated systems and pulling insights out of data. There's also forecasting. So this is the thing that people were talking about, like time series analysis. There was a question about this before the talk. There is time series analysis here, and there are many applications for it. There's nowcasting. So I mentioned that you need to balance the electrical grid, work out how much supply and how much demand there is. If you're relying on solar panels or wind turbines, the supply as well as the demand is going to be changing from moment to moment. So you need to understand how much power is going to be produced by solar panels or by wind turbines in order to match that to demand. Nowcasting is essential to work out the minute-to-minute supply of electrical power. And if you don't do this, then the alternative is that people use fossil fuel generators. Like they will have a natural gas plant, which is sort of running on standby in the background in case the sun goes behind a cloud or the wind stops blowing. And unless you have really, really accurate forecasts, you will have to be running these sort of low-level fossil fuel generators that produce greenhouse gas emissions. Forecasting agricultural yield to prevent famines and improve food security is really important, especially as droughts and other extreme events that impact agriculture take place. And then predicting prices for carbon markets. I'm not really going to go into this, but there are various incentive structures basically to cause people to emit less carbon dioxide and greenhouse gas emissions. The fourth overarching theme that we can see is accelerating simulations. So in many areas of science, and in particular in areas relevant to climate change, we have physical models of complicated systems that require really large amounts of compute and time in order to do exactly. So, for example, weather prediction and climate prediction, but also things like electricity simulations in the electrical grid. And it's really important to have fast versions of these, not because the versions that we have are bad. We have very, very good models of the climate, but if they're too slow, then we can't run them, for example, at high enough resolution to say the climate is going to change here in this particular region in this particular way. We just don't have the spatial temporal resolution because these models are too complicated and time intensive. There are particular portions of these models that can be sped up using machine learning. Machine learning is not going to go in and solve the world's climate. That's too complicated. We need the physics, but there are particular portions where an approximate model can be useful. So for example, I'm working on, with Environment and Climate Change Canada on fast approximations for radiative transfer, which is a particular piece of atmospheric physics, which is very time intensive to solve exactly. This is also useful in designing more aerodynamic vehicles where we need to basically solve the fluid dynamics of airflow, but doing that exactly can be time intensive, so having fast approximations can be useful. And likewise, again, in electricity scheduling, which is also something that I've been working on, coming up with basically fast machine learning approximations for non-convex optimization, because the exact solutions to these are just too time intensive to run, and they need to be run every few minutes if you're operating an electrical grid with lots of solar power. Final theme I want to highlight is accelerated experimentation. So this is using machine learning to speed up the process of scientific discovery itself for faster creation of next generation climate tech. And this is suggestions for which experiments to try. It's not replacing the process of scientific experiments. It's sort of saying, this might be a good material. Let's try that. Now, Edison supposedly tried like thousands of materials before settling on carbon as the material for the filament of a light bulb. Now, machine learning can speed up that process by trying fewer. You're not going to not have to have experiments, but you don't have to have as many necessarily. So this can be used for designing better materials for batteries or photovoltaics and solar panels and other applications, or more efficient synthesis methods for things like fertilizer, which by itself, just creating fertilizer around the world is 1% of all the global greenhouse gas emissions, just making fertilizer. So having a more energy efficient way, a better catalyst, for example, for this would be extremely, extremely impactful. Okay. So these are some overarching themes that we've seen for how machine learning can dial into different climate strategies. Let's think about the things to bear in mind here. The first thing to bear in mind is that in each of these cases, machine learning is only one part of the strategy. It is not solving the problem of climate change, and it's not even solving the single thing that is needed. So for example, batteries. We need more batteries so that when the sun is not shining, solar panels can still provide power. And right now we are not really able to store power when it's not being created. But machine learning is not immediately creating a better battery. It is connecting with materials science and working with materials scientists to run experiments on on different kinds of batteries to see which ones are effective in different circumstances and helping us design a better battery, but not, again, it is not a replacement for the material science. It is augmenting material science. There are many skills and tools needed to fight climate change. I'm not here to say that if you would like to work on climate change, you should be working on machine learning. There are many tools for attacking climate change. And if you are undecided how you would like to have an impact on climate change, there are many other things that I would suggest also learning, either in addition to or instead of machine learning, in fact, like policy and energy and transportation, which are all areas of study. Many areas do not need machine learning at all. There are a lot of problems relevant to climate change that don't need machine learning. For example, if you are trying to help buildings use less energy, there are smart buildings. So smart buildings are like having the building respond to the occupants. Like, there are more people in the building, I'm going to turn up the temperature or turn on the lights. And that's great. It does save energy. But an easier way to save energy is just to insulate the building properly. And so if you're building a new building, by all means, make it a smart building. But if you are just trying to sort of have a fast approach for helping climate change, insulating your building is much more important. Even in problems where you do have something that's sort of data related, sometimes simple methods are going to work. So I guess this is an overarching point, and a lot of these points are overarching, regardless of how you're trying to apply machine learning. Don't think about using the fanciest methods. Everybody, myself included, gets excited by some fancy new method, whether that is transformers, if you know what those are, or GANs. Before that was one of the big things that people in machine learning and AI were really, really excited about. And those are great in certain applications. You should always start thinking about the simplest possible method. And the reason for that is that it will be easier and there will be greater buy-in. More people will want to use it. More people will be able to use it. If you have a complicated method, it's less likely that it will actually be used in practice. And also some of the simple methods just work better. So start out with linear regression, get more complicated, and then eventually maybe you'll need an LSTM or a transformer. The impactful applications are often not sexy. Everyone hears about these fancy AI technologies, startups that are going to save the world with self-driving cars or with automated blah, blah, blah. The impactful applications may be much more optimizing freight routing, which are not really catching your imagination, but are very solidly making progress towards a particular bottleneck that is actually really impactful in the world. And it turns out that self-driving cars are actually probably going to make climate change worse. Self-driving cars are complicated. I'm not really going to go into this, but it has to do with something called the Jevons paradox, where if you make something more efficient, people often use it more. So suppose that you decrease the cost of t-shirts. Suddenly, everybody wants more t-shirts. It's already happened, I guess. The t-shirts are really cheap. So people buy a lot of t-shirts, and that means that overall, the amount of consumption has increased, even if you've made the thing more efficient. This is the case with cars. If suddenly it becomes easier and cheaper and nicer to drive a car, more people will be using cars. Now, somebody raised a comment in the chat, LED lighting. LED lighting is good because LEDs use so little electricity that switching to LEDs, even if you use those LEDs more, is still beneficial. But in the case of cars, self-driving cars are not actually that much more efficient than, from an energy perspective, than person-driven cars. There are various ways that they can be more efficient, but depending upon how we use them, and it really depends upon the policy, we may end up using more energy as a result of self-driving cars and more people driving. Now, I'm not here to diss self-driving cars. They do make cars safer. They just are not a good climate application, probably. It depends. Very much depends. Then there's incentive alignment. So it's important to remember that maximizing profit is not always the same as making something more efficient and having better climate impact. There are various examples of this, but you shouldn't basically assume that the reason why we haven't solved the problem is that systems aren't efficient enough. Here's an example. There are companies that are farming shrimp in Scotland and then selling that shrimp in Scotland. And you would think, this is really efficient. It's being eaten where it is being produced. It doesn't have to be transported anywhere. But they're actually transporting the shrimp to China to be processed and then shipping it back to Scotland to be eaten. This is not an efficiency gap. They didn't, when people in machine learning are like, let's make systems more efficient and that will solve all our problems. In this case, this is the most efficient thing to do from a cost perspective because the price of processing shrimp is lower. The cost of labor in China is lower than in Scotland. So shipping it halfway around the world is the most efficient thing from a cost perspective. So this really gets at the issue of incentive alignment. This is one of the reasons why we need policies, not just in order to say, you should do this, but also just to change the objective function, change what people are optimizing for. If there is a price on carbon, which there is in many places, including Scotland actually, but not high enough, if you have to pay for emitting more greenhouse gas emissions, then you are more likely to choose more efficient ways that are efficient in the sense of climate change, not in the sense of profit. So again, it really matters what you're optimizing for. Machine learning is really good at optimizing for stuff, but optimizing for profit is not necessarily the same as optimizing for climate impact. There's a question about self-driving cars. Is the fact that self-driving cars are more efficient comes from the fact that they are electrical? No. Electric vehicles can be is a really good question. Electric vehicles don't have to be self-driving. People often confuse these two things because Tesla is doing both, but there are autonomous vehicles that are gas-driven, and there are electric vehicles that are non-autonomous. Now, there are ways to control an electric vehicle particularly efficiently if it's autonomous. And there are also ways to control just any vehicle more efficiently if it's autonomous. For example, having a lot of vehicles drive together so that they're all sort of in each other's slipstream. Like when you see bikes racing, like bicycle racing, everybody's right behind the other person so that they sync up in air resistance. It actually uses a lot less energy to do that. You can do that with cars too, but you wouldn't want to do it if you're a human driver because there's always a chance that driving really close to another car, you crash into them. So this is a way, it's called platooning. And it's a way to make, in particular, freight transportation with autonomous vehicles very efficient, or much more efficient. But it is not because of they're being electrical. Very good question. Okay, finally, I want to say here that machine learning is not intrinsically either good or bad. Like it is not just a uniformly good thing for society. I'm not going to talk about all the ways in which machine learning is terrible for society in other ways, like, for example, perpetuating biases and making biased conclusions seem like they are objective. There are all kinds of issues with that, perpetuating it and exacerbating inequities. But one of the things I will talk about is negative applications from a climate perspective, which is including things like machine learning is being used by the oil and gas industry in order to accelerate oil and gas exploration and extraction, making oil and gas cheaper. That is directly bad for climate change. Arguably, the negative applications of machine learning are more impactful right now than the positive applications, which isn't to say that we shouldn't work on positive applications. It's to say that we should work as much as possible on positive applications and try to work as little as possible on negative applications. But machine learning is like any other technology. It just accelerates stuff. What you use it for is dictating what its actual impacts are. Okay, how should you think about working in this space? Or really working in any area of machine learning for a positive social impact. What's called AI for social good, though I hate this term. I hate the idea of AI for social good because it implies that everybody else is working on AI for social bad, which is to some extent true. So the first thing about the broader context, like where is what I'm doing living within broader climate change strategies or broader strategies for societal benefit? Understanding in particular the specific bottleneck and why machine learning is good for addressing that. It's really easy to sort of do a keyword search, like I'm working with energy, that means I'm helping solve climate change. No, you need to be working on a particular bottleneck that people already had. It's very easy to solve problems that people don't already have. And if you're solving a problem that doesn't exist, you're not actually having an impact. You might be distracting from work that is actually more impactful too, so you might be making things worse, not to scare anybody. And I'll say how to avoid these pitfalls in a moment. Think about, obviously, the machine learning methodology involved. So like what you're going to be doing. So first is like, why are you doing it? Then what are you doing? But also think of how it's going to actually have an impact. Because I mean, I often am speaking to graduate students or Silicon Valley, tech bros. And it's very easy to think, I have published a paper or I have made a startup, and that means that I am changing the world. No. In order to actually change the world, you have to make sure that what you do gets done. It's not enough just to write the paper and assume that somebody's going to find it. That doesn't happen. You need to actually think about the pathway to deployment and impact for it. And that will mean working with a lot of different people or understanding who needs to be involved. I'll get to that in a moment. And then you also need to think about general considerations for implementation, like, are there ethical considerations to using the data in this way? Are you using data that could, are you accelerating the use of private data or data that is not that should not be used in a way like this? Or are there potential side effects? Is this other potential considerations? I may get into that in a moment. So yeah, just try to think about all of these early on before you have a finished project. I can't tell you how many times I've talked to somebody who sort of created a paper and then just sort of expected it to help. And that's not how it works. You need to think about exactly what it's going to do before you create it. And this is really hard. This is one of the reasons why people don't work on applications of machine learning for societal benefit that much. But there are huge benefits of this if you do it the right way. So really the right way to do it is collaboration. If you take a single thing away from this talk, it is just, if you want to have an impact, collaborate with people, partner with people who work in the relevant area. This is extremely important because there are a lot of people who need machine learning and AI, but who don't understand it. But if you understand machine learning and AI, then there's something that you probably don't understand on the other side. And so if you work together, you can fix both of those problems. Work with, or at least talk with, a lot of people in the relevant areas. And so what does that mean? There are different stakeholders you should at least be aware of. So there are researchers in the relevant domain. Like if you're working on machine learning for applications in energy, you should work with energy researchers who understand the problems in energy. Like make sure that you're working on a problem that actually needs to be solved. But you should also be thinking about companies that deploy the technology, because exactly what you do will matter. Like if you are creating a technology that the companies that would deploy it wouldn't understand, or would not be, like, that is not accessible to them in some way, then it's not necessarily going to be useful, or there's a barrier to its being adopted. Think about the communities and the end users for which it is deployed. For example, sometimes if you are working with major agriculture companies, that's not necessarily good for smallholder farmers or community agriculture. Understand what the interests of the different people are, or try to understand. And then think about policymakers regulating the technology. This is sometimes this is more relevant in certain cases than in other cases, but in general there is that other there is that other piece to the picture. Work with these people from the start. They should be involved in the initial scoping and development of a project, as well as the deployment. Again, don't finish a project and then say, okay, how am I going to actually get this deployed? It's really important to think about that from the start, because if you bring in the people from the start, they will help create a project with you that is what they need. And so that's really that is the way to have an impact. As an example of this, so I am currently working on a lot of different projects in this space. One of them that I didn't mention, on identifying butterflies. So why is it important to identify butterflies? Well, because we need to understand how ecosystems are changing as a result of climate change and other things. And butterflies are something that people actually look at a lot. So there are millions of photos of butterflies being taken across North America, and there are a couple of central databases where people put them. But in order to use them, we need to identify what the kinds of butterflies are. And most of these people are not expert enough to do that. And there aren't enough experts to identify millions of butterflies. So I'm working together with the eButterfly project, which is a platform where people put butterflies. It has hundreds of thousands of photos. And We are currently, like right now, deploying with them a set of machine learning tools for automatically identifying butterflies based upon what that platform in particular needed, based upon their particular use cases. Now, this was innovative machine learning, but it was also very much driven by the end user. And because we were developing it together with the end user, they are putting it on their website right now, and is being used to create data for scientific discovery in understanding how ecosystems respond to climate change. Okay. If you are interested more in this space, I encourage you to check out Climate Change AI. So Climate Change AI is a global initiative to catalyze work at the intersection of climate change and machine learning. We are a network of thousands of experts from research and from industry and from policy, so all the different components of this. And we provide a lot of resources for working in this space. So that includes the report I mentioned before, Tackling Climate Change with Machine Learning. If you go to our website, you can see the interactive version of it. Tutorials, videos, stuff going into a lot more detail than I could today. So if you were frustrated that I wasn't talking about like particular research projects as much, you can find as many as you want, like videos from me and other people on Climate Change AI. And we also, there are a bunch of other resources as well. Like we provide lists of data sets and readings, and we're just launching a grants program and a bunch of other things. There is a newsletter that you can sign up for with listings of jobs in this space, including like, academic jobs and as well as industry jobs, funding, papers, data sets, many other things. There's a discussion forum online where you can actually meet people from complementary areas where, if you post saying, I am looking for people with expertise in transportation, you will find people with expertise in transportation somewhere in the world. We have events for knowledge sharing, all the major machine learning conferences, the UN Climate Change Conference, we had a TEDx event, a bunch of other things. And recordings of these events are available online. And then we also provide advice to stakeholders, like advising national governments and stuff. I encourage anybody to check that out if you are interested. Again, climatechange.ai. And I am happy to spend the rest of the time on questions and just discussing things that people want to talk about in this space. Thank you so much for listening. Questions? Points to discuss?
Well, can I start off then?
Please, go ahead.
The last point you made about collaboration and how it's super interdisciplinary, like, makes a lot of sense. But in practice, like, given that most of the people here are in CS, like, how would you recommend we go about making sure that?
Great.
Yeah.
So there are a lot of people in other departments. They exist, and they are looking for computer scientists often. There is a worse way to start a collaboration than to say, I think your work is really interesting to a professor or a graduate student in another department. Tell me more about it. And maybe we could find something which is at the intersection of computer science and what you do. I can't tell you how many professors have reached out from other departments at McGill saying, there's this machine learning thing. I want to know more about it. I think it could be useful in my work. That's not just me who can talk with them. That's also students. So that's one thing. Then you can also just take courses in other areas. There are so few people who are truly at the intersection of different things. You immediately become extremely marketable and useful to society and just like have the potential for really huge impact. If you want to be a person who is like energy and computer science or transportation and computer science, there are really few people who actually understand both sides of something like that. And if you feel like taking courses in some of these areas, that can be immensely impactful. Then sometimes, there are like internships at companies which are relevant too. And that's another thing that one could think about. I'm happy to go into more detail on any of these.
I guess like I am like pretty certain that I'm never going to be an expert on the number of topics that this touches on.
Of course not. And I'm not either.
So like how, well, I also like would like to know how you go about finding people, like the people who would benefit the most outside of like, this is an academic environment where
Yeah.
people.
Exactly. So don't think in terms necessarily of, think in terms of like what you are most interested in doing and where your particular expertise lies. You know, that could be you particularly have enjoyed reading about agriculture and, you know, feel passionate that, you know, people should be working on agriculture. Doesn't mean you have to know about agriculture, but you could decide, I'm going to try to use computer science in various agriculture settings. Do some readings. We have a bunch of readings on climate change AI, but also just in general on, you know, computer science in pursuit of precision agriculture, for example, which is making agriculture more efficient by using robots, or on agricultural monitoring, so to improve food security. Work out what crop yield is going to be, for example, from remote sensing.
What about the other way then? Is there, like, have you ever found yourself in a position where you have to be explaining like the models that
you will have to do that. It's just, it takes, if you are the one sort of proactively reaching out, you should know a little bit about the other area, enough to enough to know sort of what you need to, some of the things you need to ask, and some of the people you could talk to. Then they will explain things to you and you will explain things to them. You will be shocked by how little people understand about what machine learning and computer science really is and how basic things they need. But in order to get to the point of that, you need to know a little bit about their field, just a little bit. But it's never too early to start these conversations. Does that sort of respond to your question? I mean,
no.
In particular areas, there'll be particular companies that you can find. So for example, if you're interested in agriculture, you could say, okay, well, Indigo Ag is a company that is hiring computer scientists to work on agriculture problems. Maybe I could do an internship at Indigo. Or, you know, half a dozen more, you know, Descartes Labs or Trace Genomics or blah, blah, blah. Some of these are big companies, some of these are smaller companies. That will introduce you to a little bit to the space if you want to, you know, get your hands dirty in that particular way. Or you could talk to academics, or you could, you know, read articles, but ultimately you're going to want to talk to people.
Okay.
I don't encourage people to try to do all of these things at once. Pick particular problems and areas that you find interesting, learn a little bit about them, and just start talking to people. And you will discover more cool things. It's really important to get out of computer science silos, regardless of what you want to work on, just because the rest of the world knows so little about computer science. And once you realize just how many opportunities there are, it's really exciting.
Cool. That's a really like exciting, optimistic take on things.
There's a question about blockchain. I, for one, am not optimistic about climate change applications using blockchain in general. I've seen a lot of projects that try to use blockchain. They don't really need the blockchain. There are people who are more expert about this than I, but I've seen several projects where people think that it is, people think that blockchain is important because they don't really understand blockchain. But I'm not going to venture into that area as much because it's not something that I'm expert in. Are there applications of machine learning and AI in nuclear energy? Yes, I didn't talk about them. So nuclear energy currently means fission. That's what nuclear power plants are. Some of the applications there are in predictive maintenance. So one of the big costs in nuclear is sort of making sure that things don't go wrong. Predictive maintenance and fault detection are things that machine learning can do pretty well. So like making sure that things don't go wrong in nuclear power plants is great. Then there's really sort of out there work in nuclear fusion. Nuclear fusion is a technology that would solve all of our problems if we got it working, but it's been 40 years away for the past 40 years. And so it's not, we shouldn't wait for nuclear fusion, but machine learning is being applied to nuclear fusion experimentation to try to control the experiments better, pick experimental parameters that are good for experimenting with nuclear fusion. And that's great. I'm glad that people are working on it, but not everyone should be working on it because nuclear fusion is definitely, it's a roll of the dice whether it will work or not. Am I optimistic about climate? So I think that it's kind of interesting. I was much less optimistic about climate before I was working on climate change. I think this is generally something that I find. When I'm working on a problem myself, I don't really have the mental space to be worried about it. It's, if you're worried about something, if I'm worried about something, it's generally something that I'm not working on. There are many things that I'm worried about, but I feel least in control of the things that I'm not working on. Obviously, I can't personally control whether climate change stops or not, but at least by working on it, I feel a lot better. So I guess, yes, I'm optimistic in the sense that I think there's a lot of really good work being done. I'm not optimistic in the sense that things are definitely going to get a lot worse. Regardless of what we do now, things are going to get a lot worse. Partly because we're just locked into various negative effects. But I do think that we have the ability, I'm really optimistic about the number of people from lots of different areas coming in to learn more about climate change and how they can make a difference, and trying to use their particular tools. Like I've said a lot of caveats about why machine learning, you have to be really careful applying machine learning, but ultimately what climate change is there are a lot of opportunities to make an impact. This is a big, complicated problem, and bringing the tools that you have to bear on it is really, really important, whether those tools are machine learning or something else. There are a lot of ways to make a difference. So the big paper tackling climate change with machine learning is a big collaborative project. This question: are you currently working on another similar project? So the goal of that paper was to sort of frame the field, really. I am working on a similar sort of framing paper, which is sort of designed more for a policy-making audience in this space. But mostly I work on research papers. I'm a researcher, so I work on like machine learning innovations that can be useful in climate change. And there are a lot of ways in which new machine learning is needed. So like greater interpretability, being able to understand why the machine learning algorithm is making a certain decision. That's really important to cause climate change, because if you don't understand why the machine learning algorithm is working, nobody's going to want to use it. I talked to somebody who created a great machine learning algorithm for reducing the energy usage in a big Manhattan skyscraper. And nobody used it because they didn't understand it, and so they weren't prepared to use this algorithm. So these kinds of fundamental technologies, which people are working on from a machine learning perspective, like interpretability, really do make a difference in terms of societal impact. More generic question on research: what would be your advice to find supervisors and projects for a master's or summer research? If you mean in this area, I would consider people working on specific domain problems, potentially, but maybe in collaboration with a computer science expert. If you're an undergrad, sorry, I guess in this area there are people sort of working on both sides. There are the people who are working like in energy or land use, and they need computer scientists, and there are the computer scientists who are sort of working on projects in this space. And there are more of the former, so more people who don't know about machine learning but sort of want somebody to work on machine learning. That could be an opportunity for summer research. They wouldn't be supervisors for a master's because they're not in computer science. If the question was in general how to find supervisors and projects for a master's or summer research, my general advice for how to find a supervisor is to look for candidate supervisors to, before emailing them, sort of read a bit of their work, come up with some ideas and questions for them. This doesn't have to take a huge amount of time, but make it clear that you've done your homework, and then reach out to them sort of talking about their work. Even if these are naive questions, I can't tell you how much of a difference it makes getting an email from somebody who's done their homework and sort of really is trying to understand the thing. Even if, clearly you're not going to be able to understand the entirety of a professor's work, but if you've read one of their papers and have like genuine questions, that is so much better than just being like, I want to work with you. So that's my general advice, regardless of what area you want to work in.
All right, well, if we have no more questions, we're just coming up on time. Dr. Rolnick, thank you so much for taking the time and for giving a really cool and enlightening presentation.
Absolutely.
I'm
Thank
like
you so
super
much
psyched to hear what you're up to next.
Inviting me, and feel free to reach out if you have specific questions about particular things that I covered or didn't cover.